I want to share with you that we all had to be cognizant. So given the time period of only 20 minutes, I'm going to only focus on these three things. Understanding bias in AI, the definitions of biases, there are so many definitions, and then how to minimize or mitigate bias in AI. Especially those of you who are interested to work and you're going to be working on the AI tools pretty soon, these are something to start watching yourself even before we start. So what is the understanding bias in AI really means? The AI algorithm is a black box and they are prone to bias at all the stages. If you don't pay attention, the bias can creep it in any one stage and that can create health disparities. At the opening ceremony, at the keynote, they were telling about all the introduction of AI in medicine in the clinic, and we had to be cognizant of the biases embedded in some of these models and how to get rid of it. Especially bias may refer to unequal preference to person or group, especially a lot of the tools are developed in one region and then we try to adapt in another region. That can really impact on the outcome because there is so much biases. The thing which I want to say is like understanding bias in AI and detecting the potential flaws predisposing AI tools is a shared responsibility. It's not just the developer has to worry about, it's the user such as us has to be concerned and also pay attention for the AI development. So I am not an AI developer, but I am an AI user. It's like I see the medical physicists, most of us who are in the clinic will be the users because while minority of us may engage in data science as AI developers, there are many of us in medical physics who are doing these things, but majority of us will be exposed to AI tools and will be the primary end users of these tools in our practices. So it is important for us to understand. So under the importance of understanding the bias in AI, I just kind of put these few things together. One is deployment of AI tools in clinics are growing. Like as of now, according to the US FDA, there are nearly close to 1,000 tools has been approved, AI tools. Out of it, majority of the tools are in radiology, about 800 of them. And out of that, none of them have been approved for detection, but a lot of it for workflow and triaging and so forth. So it's very crucial at the beginning itself for radiologists or physicians, medical physicists such as yourself and others to make sure that AI, we rely on AI and when to question its recommendation. That is very key for us. As an end user, we may not be developing AI, but we need to have sufficient knowledge to question whether the recommendation is the right one or not. So that's what I am interested in helping the medical physicists to equip ourselves with knowledge so that we know when to question the right thing. That is very important. And even those of us who are not involved in algorithm, we may contribute as subject matter expert. As a medical physicist, we know our subject. When an AI tool tell out something out of the medical physics, we should be the one to tell the answer is right or wrong, and not simply blindly accept what the AI tools will tell us. And again, for this one, the context really matters because the bias, there are so many definitions of bias if you search for this in the dictionaries. Among that, there are some of the bias definition can overlap concept in different contexts. One example, for example, it has been demonstrated that an AI algorithm trained with due attention might underestimate healthcare needs of a black patients compared to those of a white patients. That's in US context I'm talking about. So the same tools come to the Asian, Southeast Asian area. Of course there will be a lot of health disparities if you simply accept an AI tool. Here's an example. This has happened a few years ago. Probably you might know a company which was trying to...
I will just make a short introduction and briefly discuss the machine learning pipeline. So the process is very long, starting with data acquisition, data pre-processing, feature engineering, model selection, model training and testing, model evaluation, external validation, model deployment. So the first part of this workflow is probably the most important, the most difficult part of the pipeline. So we usually acquire data, DICOM images and DICOM metadata, very useful. Metadata are very useful for machine learning. So we get images from PAC systems, and of course we have to anonymize this data, and it's very important to store this info in an organized way. In my institution, we have developed our medical physics packs dedicated to AI. So we store their data that will be used for machine learning, and a workstation and a network attached storage, and then we label the data set. So this is as an example, a data set with features and labels. So don't forget, this is very important, that behind AI and behind machine learning, the science is statistics, right? So in this particular example, the features are the independent variables, and the label is the thing we are trying to predict. In other words, the dependent variable. So this is a regression problem to predict, in this case, organ doses from computed tomography. So the label is the lung dose from CT, and the features are the usual suspects. The KV, MA, scanning length, pitch, and so on and so forth. And we can also label images, annotate images, if they are useful for our machine learning project. So then we have to process data. Our data are real world data, messy, noisy data. So we need to clean data because there are missing values, so some kind of imputation is needed. And then there are noisy data, outliers, categorical data, and ordinal data. Computers do not understand male, female, or medium, high, and so on. So we have to turn into this information into numbers, and some kind of normalization or data transformation is needed. So all values end up in a scale 0 to 1, for example. And then the dimensionality reduction is an important process because we prioritize, this is feature importance. So this is a process to select the most important features. Doesn't make sense to include in our models, for example, weight and BMI and water equivalent diameter. So all these three values are highly correlated. So we have to select one of those, the most important for the machine learning project feature. Then we select the model. Have to select the model. It can be regression or deep learning or whatever classification algorithm, and an open access library. This is important because some kind of coding is needed, of course. And then training, we split the data set into training and test set, and finally we evaluate, validate, and deploy our model so that other users can utilize our effort, can utilize our model to make predictions. Okay, after this very brief introduction, I will get into my slides related to doses from X-ray examinations, AI-powered predictions from X-ray examinations using personalized dosimetry. So how do we estimate patient doses from X-ray imaging? We use physical fandoms, thermoluminescence dosimetry, crystals, for example, or mathematical fandoms in Monte Carlo simulations. Lengthy processes. We actually, in my institution, we use personalized dosimetry. So we don't perform simulations on voxelized fandoms, but we create patient models, digital twins. So this in this short video, you can see the computed tomography images and the corresponding 3D distribution. So we, from Monte Carlo simulations, we get those distributions, and of course this is important information, 3D, but we have to estimate organ doses or tissue doses. We have to delineate organs, right? So this is a lengthy process. Ultimately, we need equipment-specific dosimetry, true patient-specific dosimetry, personalized dosimetry, protocol-specific dosimetry, and real-time dosimetry, rapid estimation of doses. So this is, and ideally, organ dose information can be automatically incorporated into the reporting templates, so referring physicians and patients will have complete info about their doses and risks. This is an ideal scenario, but we are almost there, with thanks to artificial intelligence. So we have taken various approaches. I will describe within the remaining time some of them. So during the next minutes or so, I will give you a nutshell. I will give you an overview of our method. So we apply masks to computed tomography images. These are DICOM images, and also to those images. So the point is to exclude voxels outside the patient. So the aim is to get info in order to construct our feature matrix. In other words, to get information about the MA, in this example, computed tomography, KB. This is easy, right? From DICOM, we can easily get information about exposure parameters or scanning length of pitch. But in this case, we also need Hounsfield units. So to get the Hounsfield units, you need to get them from the masked DICOM image, to exclude voxels outside patient, and to retrieve values from the masked DICOM image, and also from the masked dose image, because this is our label. This is our independent variable. So this is our ground truth. Okay. The purpose is to create your training data set. The data set you need for training purposes. And then for body CT, this is again an example. You need to include a feature related to body size, either weight or water equivalent diameter, because those depend on body size. So in this case, we have included water equivalent diameter to calculate automatically, because this is the point, to get real-time info. To calculate water equivalent diameter, again, you need to apply masks to CT image. So this is important, because for the water equivalent diameter, you need to calculate the axial area. So this is the product of the number of patient voxels retrieved from patient mask, and then you need also the X and Y dimensions of each voxel. This can be retrieved from the DICOM header information. And to calculate water equivalent diameter, you also need to get the mean Hounsfield unit of each slice. So this can be retrieved from the masked CT image. Again, this is a long process. And the first step is to create your training set, and then you split your data set. And this slide shows some technical parameters. I won't focus on this to save some time. So this is where we are, an automated process using AI to predict organ doses for more than 30 organs and tissues. Again, this is an automatic process which includes segmentation of organs. We have documented this work with various papers. This was our first paper for head CT in European radiology, medical physics for chest CT, and then these two are very, very recent, published a couple of months ago in physics, in the European Journal of Medical Physics and the European Radiology. So these two papers describe the automated machine learning based methodology for personalized dose prediction, dose assessment in body CT. Results: percentage differences between doses produced during using the deep learning model and Monte Carlo simulations. Very good. We are very happy with the agreement. So differences in head CT lower than 5%. This is the evaluation of the segmentation models. Again, these scores are very good. So we are also happy with the segmentation based on UNet, as almost always, and organ doses estimated with using DNNs, neural networks, and Monte Carlo simulations. Difference is always lower than 20% for body CT. So for diagnostic radiology, these results are quite satisfied. And this is another approach. Generative AI is shaking up the world. It's a very rapidly moving field. And a few years ago, we started using generative adversarial networks, GANs, peaceful GANs. So there are two networks here. The generative network, which generates a fake image, a plausible image, and then a discriminate network that tries to differentiate between the fake image and the real image. And this is a binary classification problem. So the two networks are trained in tandem. So gradually the discriminate network learns to not discriminate between generated image and real image. It means that the fake image is as good as the real image. So this is the goal. And these are some results. This work has been published. It was published actually 1 or 2 months ago in the European Journal of Medical Physics. Excellent, unbelievable results. So the ground truth, which is those images from Monte Carlo, and then the synthetic images, the fake images, which are very, very similar to real images. So the GANs learn how to produce synthetic images, which are as good as the real images. Another work on CBCT in radiotherapy, how to predict organ doses, and this part of this work was used to has been incorporated into iDose. iDose is a very new platform, so it is web-based. It is free, so registered users can use iDose. iDose, this is the URL address. So there is a toolbox with 3 tools: the iDose Diag, the iDose RTI, and the iDose AI. So the iDose Diag and iDose RTI are based on conventional dosimetry. There is no AI here. So our methodology is based on normalized doses as a function of water equivalent diameter, again without any AI involvement. The third tool is the iDose AI, and we have deployed at the moment 4 models. So deployed means, once again, as I said, that others can, we have a graphical user interface, so others can use our models to make predictions. Of course, there are various challenges, technical solutions, and benefits. So there are opportunities, and as we all know, various challenges. Mahesh has already described extensively bias, discrimination, but there are also many other challenges. Lack of regulation, for example, is another. Well, we can discuss them later. I will be happy to answer your questions. So with that, I would like to thank you.
Thank you, John. Yeah, we'll wait for the discussions later. So our last speaker will be Dr. Hidetaka Arimola. He will be discussing the AI-based.
To answer your question, that's an excellent question. You are telling that in LMIC countries, collecting data is very difficult. It's also difficult everywhere right now. Every AI vendor is having that issue. Companies are developing tools. The first question you can ask is like, what is the database data collection models? You'll be surprised how small the models are sometimes. So that's also one of the reasons why we are seeing so many tools being produced, but none of them been accepted yet, because it needs millions of data points. So the issue of collecting the good data is going to be a challenge everywhere. So right now the issues coming out is like for example, there is a project with AAPM is involved with the American College of Radiology and RSNA called Materi data. This is supported by the national funding, and this particular group is what we are trying to do is like develop data sets which anonymized and cleaned so that any other researchers can use this data to develop it. To answer your question, will that same data apply based on the anatomical differences? Will it apply everywhere? There will be a challenge. However, the outline will be the same thing. So the variation is with the size, color, and everything will change, but the outline will be the same. So if the data developed, which is overall clean data, anonymized, has wide diverse data set, those data set will become very valuable for developing any tools. And we're going to see that, and there are efforts being done. I think those efforts are very essential to creating a data repositories. I think the same thing can be done in the Asian region to have associations or governments to create data depositories. When it means data depository means people are supplying their data, and third party, independent party will clean up the data, and everybody can use it to develop the tools. And it's not as easy as I say. It's very difficult. And one project, that's what we are doing at the APM, is this particular large group, and they have now developed a CT data set for chest CT and brain CT and everything. These data sets are now allowed freely for anybody to use this. So the user developer can use these data sets to develop a tool. I think that's the direction it has to go, because there's no one can produce all the data, but those who provide good data will be the leading effort of this one.
High quality.
High quality.